the gentleman who will be speaking with us today is Steven Weinberg, who holds the Josey Regental Chair in Science at the University of Texas, where he is a member of the Physics and Astronomy departments. He is the author of more than 300 articles on elementary particle physics, and his research has been honored with many awards, including the 1979 Nobel Prize in Physics, and in 1991, the National Medal of Science. His books include, for popular readers, The First 3 Minutes, which I've read and I loved, Stephen, Dreams of a Final Theory, The Search for the Fundamental Laws of Nature in 1993, Facing Up, Science and Its Cultural Adversaries, 2001, and his most recent professional book is Cosmology, which came out in 2008. He also has just, I'm proud and gratified to say, joined Scientific American for its board of advisors. And so with that, I welcome Steven Weinberg. Thank you very much.
Thank you. Good morning. In a few months before the end of the year, there will begin operations at what will be the largest scientific instrument ever built, the Large Hadron Collider. It's located in Switzerland, well, actually on the border between Switzerland and France. The border runs along here, separating the blue from the green. And this circle is approximately the size of the supercollider. It's 27 kilometers. Okay, thank you. It's 27 kilometers in circumference. It is run by the Pan-European laboratory CERN, which is headquartered just outside Geneva. Inside the accelerator, well, this is a tube running underneath the Earth, under the Jura Mountains. Inside this tube, there is an evacuated series of magnets which bend a beam, in fact, 2 beams of protons that go round and round in opposite directions, being accelerated by electromagnetic fields up to a higher energy than has ever been achieved artificially here on Earth. The design energy was 7 trillion electron volts in each beam. That will not be reached. And as I'm sure most of you know, a trillion electron volts is approximately 1,000 times the energy contained in the mass of a hydrogen atom, according to Einstein's E equals mc squared. So this is 7,000 times that. That energy will not be reached at first because of an accident that occurred last year. It's necessary to start slowly and build up confidence that this machine is really operating the way it should. But that's the goal. I was there at CERN in July and had meetings with the director and the people who run one of the largest detectors at CERN, the so-called Atlas detector. And I didn't find any lack of confidence that they would eventually reach this design energy, although there's a lot of disappointment that it's taking so long. Excuse me. Yes. Oh, I'm sorry. Yeah, I keep forgetting.
There's a streaming video.
It sounds so loud to me, but I will try to remember to use. So I have to hold the mic in one hand and this in the other hand. Okay. There are 2 beams because if you fire a beam of high-energy particles into a stationary target, most of the energy just goes into producing the recoil of the target, which is not interesting. And so today, increasingly, these accelerators are designed to have 2 beams which collide head-on. In that way, there is no net momentum, and all of the energy available goes into producing new matter. And that's the point, that again referring to the famous E equals mc square, to produce a certain mass m, you need a certain energy E, and we believe there are exciting new particles to be discovered with masses so large that no previous accelerator had the energy available to produce them. Now, I'm not an accelerator designer. In fact, if you have any questions about what went wrong with the accident that occurred last year, I'm probably not going to be able to give a very authoritative answer. I'm a theorist. My business is that of a consumer of what comes out of this accelerator, data about new kinds of matter. And I have ideas about what is likely to be found. In fact, I would say, as is very often the case with accelerators, there are some things that we think are likely to be discovered, and we'll be very surprised if they're not. There are other things that may be discovered. We have a whole menu of possibilities, and we're very alert to those. And then there's also the possibility that something is discovered that nobody anticipated. And it's the first two that I'd like to talk about. The third, it's a little bit difficult to talk about for obvious reasons. In order to do this, one has to do this in the context of what we already know. What we already know about the nature of matter and force is crystallized in what is called the Standard Model of elementary particles. It's a theory of all of the particles we observe, and with the exception of gravitation, all of the forces that act among them. It's a theory that was developed in the 1960s and 1970s, and then through a series of experiments in the 1970s and 1980s became well established as part of the standard canon of scientific knowledge. In the Standard Model, oops, I didn't mean to do that, I meant to do this. The known particles are these. There are ordinary matter is composed of two kinds of quarks and electrons. That all the yeah, there it is. Thank you. You see what goes wrong with accelerators. All ordinary matter, atoms, molecules, people, stars, galaxies, are composed of just two types of quarks and electrons. There are also neutrinos, which are continually being emitted by stars in the course of the processes that produce their energy. In addition to these particles, there are heavier particles which don't appear in ordinary matter because they're so heavy that they're unstable and they decay into the particles I've mentioned, electrons, neutrinos, and the two lightest types of quarks. There are heavy quarks, in fact, a total of 6 types of quarks, and the electrons have siblings, particles that are very similar, except they're much heavier, called muons and tauons. The forces between these particles are transmitted, first of all, by photons, which carry the electromagnetic force, and much heavier particles called W and Z, which transmit a related force, very closely related force, called the weak nuclear force. There are also, although for some reason I left it out here, particles called gluons, which transmit the strong nuclear force, which holds the quarks together inside the neutron and proton, which are inside atomic nuclei. There is a strong family connection between the photons, the W and the Z. The gluons are separate. They are not related in any simple way to these, but they all share the property that they have the same spin. Spin is the quantity which in learning classical mechanics is called angular momentum. It's just a measure of how fast something is spinning, how much is spinning, and how big it is. One of the principles of quantum mechanics tells us that the spin always comes in multiples of Planck's constant. The multiples are 0, no spin, or 1/2, or 1, or 3/2, and so on. And these particles are categorized by their spin. The electrons, neutrinos, and quarks all have spin 1/2, which means 1/2 of Planck's constant. The photons, W, Z, and gluons all have spin 1. Now, all of these particles in the simplest version of the Standard Model, and by that I mean the version where in the equations you see explicitly the symmetries that connect the photons to the W and Z and connect the electrons to the heavy partners of the electron and to the neutrinos, and connect quarks to each other. In the simplest version of the Standard Model, these particles are all massless. That's what makes it an elegant theory. The symmetries do not allow masses, and at the level of the equations of the theory, the symmetries are manifest. When you look at the equations, you see that the W and the Z and the photon are appearing in exactly the same way. Something intrudes to break that symmetry and gives some of these particles masses. It gives the W and Z, they're very large masses, almost 100 GeV, 100 times the mass of the proton. It splits the electrons, which have some mass from the muons and tauons, which are much heavier, and gives the quarks a variety of masses. That something, we believe, is another kind of particle called the Higgs particle, which has no spin, so it's in a column by itself. This was proposed as a mathematical possibility without reference to any particular theory of nature by a number of authors, Peter Higgs, but also at the same time Braud and Angler and Guralnik, Hagen, and Kibble, who have all just, I found on an email message a couple of days ago, shared this year's Sakurai Prize for this innovation. This mathematical idea was brought into the theory of the weak and electromagnetic interactions, the fusion of the photons with the W and Z in the late 60s by myself and independently Abdus Salam. And the particular particle being sought at the LHC is the one that first appeared in these papers in the late 1960s. That is something that is definitely expected to occur. And in a way, it would be much more exciting if it isn't found than if it is. The theory of Salam and me was quite precise about the interactions of this field. We know exactly how it interacts with the electron and the muon and the quarks. It was silent as to the mass of the particle. There was an expectation it would be somewhere in the range of 100 or 200 or maybe 1,000 GeV, but there was nothing in the theory that really pinpointed any particular mass. In the years that have followed, there have been a number of calculations of the properties of these known particles, which are affected slightly by processes in which Higgs particles are emitted and then reabsorbed, never really becoming real, but still, through their virtual presence, affecting the mass and other properties of these particles. And from the comparison of these calculations with observations, theorists, not including me, this has been a long and very detailed story, have concluded that the Higgs is almost certainly in the range of 100 to 200 GeV, well within the reach of the LHC. And in fact, the LHC, although certainly it would be ridiculous to say it was designed specifically to discover the Higgs particle, the LHC, in its design, that was one of the requirements, that it had to have enough energy and intensity to be able to produce this particle. It won't at first, probably, when it runs at reduced energy, but eventually we expect that it will. Somewhat paradoxically, the heavier it is, the closer it is up to the upper limit of where we expect it, 200 GeV, the easier it will be to discover, because it will have clearly visible decay modes. The Higgs, of course, being as heavy as it is, will be unstable. No one will ever see a track of a Higgs particle. What we will see is its decay products and infer from that the fleeting presence of the Higgs particle. It has a variety of possible ways of decaying, and the ones that are most visible and recognizable are only available if it's fairly heavy. If it's lighter, more of them will be produced, but they'll be much harder to recognize. The Large Accelerator at Fermilab has already ruled out part of the range of relatively heavy Higgs, but it doesn't have the energy and luminosity to study the full range, and probably the Higgs, sorry to say, probably the Higgs will be discovered at CERN rather than at Fermilab. If the Congress had not had the imbecility to cancel the superconducting super collider, it would have been discovered long ago here in Texas. Now, that's something we expect. And when I say expect, I don't mean we're certain. All we know for sure is that there is a symmetry between photons, W's and Z's, it's the same symmetry among different types of quarks, among electrons and neutrinos. When I say a symmetry, I mean if you write down the equations and you perform certain mathematical transformations on the symbols in the equations that have the effect of turning W's, Z's, and photons into each other, and electrons into neutrinos, and quarks of different types into each other, then the equations do not change their form. We know that that symmetry is there. It's been very well verified by any number of observations. We know that symmetry is somehow broken by something, and we say it's spontaneously broken because it's not a failure of the symmetry in the equations. It's the fact that the symmetry is not satisfied in the solution of the equations. The simplest picture, and the one that produces the least conflict with other things we know, is this simple elementary Higgs particle. But there are other possibilities, and one of them, so-called Technicolor, which posits the existence of a super strong force, much stronger than the ordinary strong nuclear force, carried by particles called I won't pursue that, technigluons that act on the language gets silly. In that picture, there really isn't a Higgs, but you have a whole variety of other particles that are bound together by this extremely strong force. That's a possibility, and there's some theorists, it was a possibility first suggested by in 1979 by Leonard Susskind and myself independently, I don't think it's likely that that's what's going to be found, because it leads to problems. There are observations that you could only understand by tinkering carefully with the theory to make it right, so that it begins to look like Ptolemaic epicycles. And I don't find it as attractive as the original simple picture. But it's a possibility, and we have to remain open to that possibility. That's why it's not a sure thing that the Higgs will be found, but it's highly likely. Then there are other possibilities which are only speculative, which we have no confidence about, and but which would be extremely exciting. And one of them, and I think the best motivated of all the other possibilities, is called supersymmetry. This is a symmetry, well, it has roots in the Russian literature, which no one was reading at the time, but the people who posed this in a form that made it exciting to the physics community were Julius West, who unfortunately recently deceased, and Bruno Zimino, still with us at Berkeley. Supersymmetry is a symmetry which operates, if you like, at right angles to the symmetries I've been talking about. The symmetries that I've been talking about act vertically. They only act among particles of the same spin. So that, for example, there is a symmetry that connects the photons with the W and the Z and connects electrons with neutrinos, but never connects particles of different spin. Supersymmetry connects all the known particles with particles that are much heavier, so that we can understand why they're unknown, but that have different spin. And this is the same picture, but with the supersymmetric particles, the partners, put in. There are photons, which have spin 1. There are also particles that, like neutrinos, have spin 1/2, called photinos. And supersymmetry produces a deep mathematical connection between these particles. For W's and Z's, there are wenos and zenos. You can see the linguistic rule, but that's if you have a spin 1/2 superpartner, you put in eno at the end. If it's a spin 0 superpartner of a spin 1/2 particle, you put an S at the beginning, S for scalar. And so there are electrons and selectrons, positrons and suppositrons, neutrinos and sneutrinos, and so on. I once talking to Murray Gell-Mann, and he said this was a slanguage, and I said, no, it's a languino. But that's fun, but it's really quite serious, and it's one of the things that's so attractive about it is that for years and years it was thought to be impossible to have a symmetry that united particles of different spin. There was a theorem called the Coleman-Mandala theorem, named after Sidney Coleman and Geoffrey Mandala, that seemed to rule out this as a possibility at all, that any such symmetry would conflict essentially with special relativity. And then it was realized that there was a technical exception that allowed for this, and into that tiny little gap, Wess and Zimino went roaring and invented this essentially unique symmetry. I want to emphasize that the minds of physicists can think of all kinds of possibilities, and when we speculate aimlessly, the results are likely to be not very interesting. It's when there are physical principles that narrowly restrict our speculations so that new ideas can only take one or a very limited number of forms, that we begin to think that we've discovered something that is an opportunity that nature probably didn't pass up. And most of us have this feeling about supersymmetry. There's another reason for being excited about supersymmetry, which came along later. There is a calculation done soon after the formulation of the Standard Model by Howard, Georgie, Quinn, and me that shows that, oh yeah.
I'm sorry.
Sure. That shows that the strength of the weak, strong electromagnetic forces, which are quite different at the energies where we observe them, vary with energy very slowly so that they come together at a very high energy, something like 10 to the 15 GeV. But they didn't quite come together precisely right. Then Howard Georgie and Savas Dimopoulos pointed out that if you include supersymmetric particles in the picture, they come together quite remarkably, accurately. And this many of us take as a clue that these supersymmetry particles really are present. Unfortunately, none of that really tells you about their mass, and we simply don't know whether the Winos and the Zenos, for instance, are several times heavier than the W and Z, or 10 times heavier, or 100 times heavier. They've got to be heavier. And by the way, it's not unnatural that they're heavier. Our statement that they're heavier is not just our way of sweeping them under the rug to excuse ourselves for not having discovered them yet. The symmetries of the Standard Model, as I mentioned earlier, would make the W and Z and electrons and neutrinos and quarks all massless if it weren't for the action of the field of which the Higgs particle is a manifestation. There is a symmetry in the theory that dictates that these particles should be massless, and it's only because that symmetry is broken that they have a mass. That symmetry, however, does not make the Winos, Zenos, electrons, neutrinos, and quarks massless. It allows them to have any mass. And so they don't need the Higgs to give them a mass. They could have any mass you like. And so, in particular, they could have a very large mass. And so it's quite natural that they would be much heavier than these other particles. There would be no reason for them, for example, to be lighter. By the way, the only particle in the Standard Model whose mass does not arise from the breaking of the symmetry is the Higgs itself. And there is a real mystery why the Higgs is not much, much heavier than the other particles. And it's not. I mean, there is a quark, the top quark, which is probably heavier than the Higgs. We don't know the mass of the Higgs yet, but the top quark mass is at the upper range of what we expect for the Higgs. So why, by the same argument that I just used for the supersymmetry particles, why isn't the Higgs particle much heavier than all the other particles? And supersymmetry provides a possible answer. And that's a third reason why we're excited about supersymmetry. Supersymmetry is paired, the Higgs particle is paired by supersymmetry with particles of spin 1/2 called Higgsinos. And there are symmetry principles that can keep Higgsinos light, so that the Higgs particle would also have to be light, except for the effect of the breaking of supersymmetry, which, like the other symmetries of the Standard Model, has to be spontaneously broken. So that's another plus for supersymmetry. It's a solution to the so-called hierarchy problem. Why is there such an enormous hierarchy between the masses of the particles in the standard model and the very, very high mass scale, 10 to the 15 or 10 to the 16 GeV, where all the forces apparently are united, the answer may be that there's some symmetry that keeps the Higgsino light. We can imagine such symmetries. We can't imagine it for the Higgs itself in the absence of supersymmetry. But in the presence of supersymmetry, any symmetry that keeps the Higgsino light will also keep the Higgs light, and then that mass determines the masses of all the other particles. So the fact that there is a huge disparity between what's sometimes called the grand unification scale, where all the couplings become equal, and the scale that we measure in the laboratory may be due to supersymmetry. I have to say, though, that no one has found a completely satisfying, detailed theory of how this comes about. And that, so that there isn't any one standard supersymmetry theory. And that means either we're missing something about supersymmetry, which will be revealed to us when it's discovered, or the whole idea is wrong and it won't be discovered. And we just don't know. But this is certainly one of the targets for the LHC, and I would say it's the most important target. I'd say it's the most important target, even including the Higgs. In fact, if many of us are terrified that the LHC will discover a Higgs particle and nothing else, because that would really give us that would just confirm the standard model in its simplest form. And what we really hope is that we'll see something that goes beyond the standard model, and the number one candidate for that is supersymmetry. Now, supersymmetry is also exciting for another reason, and that it offers a candidate for the dark matter. Among these particles, the gluinos and xenos and photinos, it's very likely that one of them is the lightest of all these superparticles, all the particles shown in red on this slide. That particle would be electrically neutral and stable. It wouldn't interact much with ordinary matter. It's electrically neutral, so it wouldn't have electromagnetic interactions. It doesn't have the strong nuclear interactions. It has weak interactions like the interactions in neutrinos, but those are very weak. It's a perfect candidate for the dark matter. But to explain that, I have to say something about why we think there is dark matter. And that is what I'll do with the rest of my time. Yeah, well, I know, but the first hint, well, yes, I've already made the point that all ordinary matter is composed of protons, neutrons, and electrons. The atoms are made out of these things. The hydrogen atom is a proton and an electron. Heavy hydrogen, or deuterium, is a proton, a neutron, and an electron. Helium is 2 protons, 2 neutrons, and 2 electrons, and so on. That's what we call ordinary matter. And in fact, what I've shown here is by far most of the ordinary matter of the universe is in the form of hydrogen and helium. Everything else is a less than 1% contamination. Now, we can estimate the total amount of all matter in the universe from its gravitational effects. We can also estimate the total amount of ordinary matter. And that's a somewhat indirect argument that is not done by counting atoms, but is done by figuring out what was going on in the first few minutes of the universe, which in the formation of hydrogen and helium, which is critically dependent on how much ordinary matter there is. And it turns out that there's much less ordinary matter than all matter. We don't see what's missing, so we call it dark matter. Now, why is this not advancing? Oh, did I do something here? This is what happens to me at home when I'm always.
If you like, just tell us when to advance.
No, it's fine. Now, talking about the total density of all matter, we estimate it from let me back up. Yes, the original estimate was made by Fritz Zwicky in the 1930s by observing clusters of galaxies, like this picture of the Coma cluster, and observing how the galaxies are moving. They have to be held together by the force of gravity. So seeing how they're moving and how big the cluster is, you can figure out how strong the force of gravity is in the cluster, and therefore how much total matter, all matter, whether it's ordinary matter or not, produces gravity. So you get an estimate of the amount of total matter. And actually these days it isn't done by observing the motion of galaxies, it's observed. What you observe is the motion of hot gases, as you tell from X-rays, but X-ray astronomy didn't exist in Zwicky's time. And it's found that the total amount of matter, of all matter, in a galaxy like in a cluster of galaxies like the Coma cluster is about, well, in this one, it's 260 times the mass that you would expect from the luminosity. That is, if the cluster of galaxies was made out of stars, which are like our sun, had the same luminosity per gram as our sun, then from the luminosity of the cluster, you could figure out the mass. And the actual mass, as determined from the gravitational field, is over 200 times larger. So that shows you right away that there's a lot of mass in galaxies that is not luminous matter like the sun. Now, from the measured mass per luminosity, if you assume that's typical of the whole universe, and then you observe the luminosity of the universe, you can figure out the mass per cubic centimeter of the universe containing everything, whether we observe it or not, whether we see it or not. And it comes out to be this number, 2 times 10 to the minus 30 grams per cc. And then we ask, well, could this be ordinary matter? And the answer is no, as I said, because of cosmological nucleosynthesis. The processes that go on, proton plus neutron forms deuteron plus radiation, deuteron plus deuteron forms helium-3 plus neutron, and so on. These processes, the rate of these processes depends on how much matter there is. And if there isn't enough matter, they don't go through to completion, and they leave an unburned ash of deuterium that hasn't been processed into helium. And so from the amount of deuterium left over, we can estimate the mass density of the universe at the time these processes were occurring. And we know what the mass density is now. We know how much the universe has expanded since then. So if we know the mass density then, we can figure out what it is now. And it turns out that the mass density of ordinary matter, as estimated from cosmological nucleosynthesis, is this number, about 4 times 10 to the minus 31 grams per cubic centimeter. It's mostly hydrogen and helium, as I said. Stars and gas make up only about 0.5% of ordinary matter. And, even with this being highly uncertain, it's clear that the density of all matter is much greater than the density of ordinary matter. The ratio is the ratio of 2 times 10 to the minus 30 to 4 times 10 to the minus 31. which is about 5. Well, that ratio is 5, but the number is actually about 5. We can do much more accurate measurements with, by using observations of the microwave background. And the most beautiful measurements so far have been done with the Wilkinson microwave anisotropy probe, which is shown here, about 1 million miles from Earth. Of course, it's an unmanned satellite, like all serious science is done by unmanned observatories. That's a necessary thing. There's a new satellite which has been sent up by the European Space Agency just in the last month or so, called the Planck satellite, which will do much better than this. This observes the microwave sky and measures the temperature as a function of position in the sky, and observes a very tiny, greatly exaggerated in this picture, a very tiny fluctuations from point to point. These red spots are relatively hot, and the dark blue spots are relatively cold, but it's only about 1 part in 100,000 difference in temperature. The sky is remarkably uniform, but the observations are good enough to tell this. From this pattern, which is affected by the gravitational field of the universe, and is also affected by the speed of sound at early times, which is affected by the density of ordinary matter, we can read off by an amazing theoretical process the density of ordinary matter and the density of all matter. And the numbers are not very different from those given by classical astronomy. And the ratio is not 5, it's 5.77. These measurements are good enough, and the theory is reliable enough, so that we can actually quote a number like this, 5.77, with a straight face. It might be 5.75 or 5.80, but that's within a certain specified uncertainty. It's really something like that, a little bit under 6. Now, what's missing is dark matter, and we don't know what it is. There's further evidence that dark matter is real that comes from observations of a cluster of galaxies called the Bullet Cluster. It's actually 2 galaxies that have collided and are now rushing apart. The red shows, these are false colors, of course. The red shows X-ray emission, and wherever it's red, that means there's hot gas emitting X-rays. The blue shows regions where whatever is present is bending the light from more distant galaxies, producing so-called gravitational lensing. And so where it's blue, that means that there's a lot of matter of all kinds, not necessarily ordinary matter. And you see what has happened is that in the collision of the 2 clusters of galaxies, the hot gas has run into each other and has not gotten very far apart. It's collided, and it's penetrated, but it's been slowed down by the collision. Whereas the dark matter, because it doesn't interact with anything, has sailed right through. It is now moving away at a much higher speed than the hot matter. This is vivid evidence that there is such a thing as matter which is not interacting the way ordinary matter does, and is hence dark matter. By the way, these galaxies have also moved with the dark matter, because galaxies are small enough so that there's very little chance of their colliding. So the cloud of galaxies also whizzes, the 2 clouds of galaxies also whiz through each other. It's only the gas that collides. And so there are a lot of galaxies here, very few here, because the galaxies have just moved on past. Things like this you're not supposed to look at. Those are foreground stars. So that's vivid evidence for the existence of dark matter. And we can catalog the various properties dark matter has to have. It has to be weakly interacting, in particular no electric charge, or we would have seen it and it would have collided in the formation of the bullet cluster. These particles have to be stable or they would have disappeared by now. They'd better annihilate in pairs because otherwise there'd be too many left over from the Big Bang. And the picture is that they stop annihilating when the expansion of the universe has made their density so low they can no longer find each other. This is a calculation first done by Ben Lee and me in the 1970s. And the good news is that supersymmetry provides a, well, actually, you can figure out what the mass of these particles is likely to be from the condition that their annihilation rate is such that the mass density is what we observe. And that gives a mass in the range of 10 to 100 GeV. So although we have no a priori theoretical reason for believing they have any given mass, there is an indirect astronomical evidence that they have a mass in the range of 10 to 100 GeV where they can be found. Now, there are various ways of trying to find them that are somewhat passive. We can observe annihilation products from their annihilation in the galaxy, the sun, and so on. And there's a whole host of X-ray and gamma-ray observatories that have looked for these annihilation products. We can observe the dark matter particles from space hitting atomic nuclei in laboratories on the Earth. And again, there's a whole host of underground observatories that are looking for signs of dark matter particles hitting them, or we can create them in the laboratory. And this brings me back to the LHC and the point that I particularly wanted to make, that the that these particles, some mixture of the photinos, winos, and xenos, provides a natural candidate for the dark matter. It's quite natural for its mass to be in the neighborhood of 10 to 100 or 1,000 GeV. We have really no good idea what the mass really is. And these particles have that property, at least the lightest one is stable because there's nothing it can decay into that's lighter, so that there'd be energy available in the decay process. And yet, although they're stable, they do annihilate with each other, which is what's needed to bring their density down to what is observed, what we think is observed astronomically. I can't imagine anything more exciting and more gratifying than for the Large Hadron Collider to discover particles artificially created, which in their natural state form the great bulk of the mass of the universe. 5/6 of the mass of the universe would be in these particles. That was the headline. Thank you.
I think we have time for a couple of questions, if anybody would like to ask them, if you wouldn't mind coming up to one of the mics. Yeah, turn it on, it might not be on.
Hey, do you want this?
Okay, I think it's on. Tom Siegfried from Science News. The LHC has the potential, as you outlined, to possibly discover the Higgs and solidify the Standard Model, possibly solve dark matter. But 25 years ago, I heard you give a talk about going farther than that and the complete unification of the three forces in the Standard Model with gravity, and you talked about superstrings. And you didn't mention that today, and I just wondered what your thoughts about superstrings have are now compared to what they were 25 years ago when it was an exciting new development?
Well, the question was about the prospects for superstring theory. It's been with us, you're certainly right, for 25 or more years. It's developed mathematically, but not to the point where there is any one theory, or to the point where if we had one theory, we would know how to do calculations to predict things like the mass of the electron or the masses of the quarks. So I would say, although there has been theoretical progress, I find it disappointing. One of the hopes would be that the LHC would provide a clue to something we're missing in superstring theory, and I think there supersymmetry is the most likely place to look. One of the troubles with superstring theory is that although in a sense the theorists think there's only one theory, there are an infinite number of approximate solutions of it, and we don't know which one corresponds to our world. But at least in a large variety of the solutions of superstring theory, there is supersymmetry visible at low energies. And if we see supersymmetry at low energies, the superstring theorists may be able to derive from it some kind of clue as to how to solve these theories. But I haven't talked about it in this lecture because I don't see how that would work. It would be, I couldn't say that that was likely with any sincerity. And certainly the LHC and any other accelerator that we can imagine being built will not get up to energies which are high enough so that we can directly see the structures that are described by superstring theory, the strings or the D-branes or whatever it is. Those will not be accessible at the LHC. So any clue we get will be very indirect. I was working on superstring theory in the 80s and gave it up because I moved into cosmology, which in the last couple of decades has had the excitement that elementary particle physics had in the 60s and 70s, a wonderful coming together of theory and observation. And, cosmology now reminds me of the excitement that I felt when I was younger and doing particle physics. And it's a pity that superstring hasn't developed better. I still think it's the best hope we have. I don't know of anything else. My own work very recently has been trying to develop an alternative to superstring theory as a way of making sense out of quantum gravity at very high energies. But even though I'm working on this, I still find superstring theory more attractive, but not attractive enough.
Thanks.
Last question then.
All right. Well, I was going to ask Tom's question, but I'll substitute something else.
Think of another question.
Yeah. When dark matter particles annihilate, would you expect to see photons as the product? And if so, shouldn't we expect to see some of that in a collision of two galaxy clusters?
Yeah, that's a good question. The dark matter annihilation rate is so small, you would not see very much of it in these very diffuse clouds of dark matter that are colliding when you have clusters of galaxies. The people who are looking for particles coming from dark matter annihilation are hoping to find it from places near us where the dark matter is concentrated gravitationally, in particular maybe in the sun, maybe in the center of our galaxy. So they hope and although dark matter annihilation probably wouldn't produce photons directly, it would produce particles like quarks and electrons, which would then radiate photons or decay into photons. So we would expect to see high energy photons or electrons or positrons coming perhaps from the sun or from the center of our galaxy. But from the very diffuse cloud of dark matter, from a very distant object like the bullet cluster, we wouldn't see anything. But it's something one has to check, and you're right, one should check that. Okay.